August 28th, 2019. Mount Lemmon Sky Survey in Arizona picks up a fuzzy dot moving against the stars. They call it Atlas, just another space rock, right? Wrong. This thing came from outside our solar system, only the second interstellar visitor we've ever caught. But here's the twist that changed everything. Hidden in old telescope photos, years before anyone knew Atlas existed, astronomers found something that rewrote the entire story. You think you know how we discover comets? Amateur stargazers, dedicated surveys, fresh observations? But what happens when the real discovery happened years ago and nobody knew it? What secrets were sitting in archived telescope data while Atlas blazed toward the sun? And why does finding these pre-discovery images matter more than the discovery itself? If you value documented space exploration history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's JPL database and the Minor Planet Center. Now back to the story. Atlas wasn't just any visitor. 2.5 miles wide, hyperbolic orbit, coming in fast at 44 kilometers per second relative to the sun. The numbers told the story. This thing came from the constellation Lynx from interstellar space, traveling for millions of years before entering our neighborhood. Only the second confirmed interstellar object after Oumuamua in 2017. But here's where it gets interesting. While astronomers celebrated the fresh discovery, data miners started digging. They had a weapon most people don't think about: archived survey images going back years. Telescope surveys take thousands of images every night. Most get filed away, processed for their original targets, then forgotten. But if you know exactly where to look and when, you can find ghosts. September the 29th, 2019, astronomer Robert Warwick announces something remarkable. He found Atlas in Catalina Sky survey images from December 2017, nearly 2 years before the official discovery. There it was, a faint streak against background stars, moving at the exact predicted speed and direction. Nobody had noticed because nobody was looking for it yet. But that was just the beginning. Teams started systematic searches through other archived surveys: Spacewatch, Linear, NEOWISE. Each archive represented thousands of hours of telescope time, millions of images, years of data. The hunt was on. December 4th, 2019, breakthrough. Astronomer Davide Farnocchia and his team at JPL announced they found Atlas in images going back to 2016. 3 full years before discovery. The comet appeared in 38 separate observations across multiple surveys. Suddenly, instead of a few months of data, astronomers had nearly 4 years to work with. Why does this matter? Because orbital mechanics are unforgiving. To calculate where Atlas came from and where it's going, you need precision. Every observation point adds accuracy. With just the post-discovery data, astronomers could estimate Atlas's path with decent confidence. With 4 years of positions, they could nail it down with surgical precision. The math worked backward like this. Using all the pre-discovery observations, astronomers calculated Atlas's orbit with an accuracy of less than 1 arcsecond. That's like hitting a dime from 2 miles away. They could trace its path back through the solar system, back to interstellar space, back to its origin point in Lynx constellation approximately 4 million years ago. But orbital precision wasn't the only payoff. More observations meant better physical characterization. Atlas brightened dramatically as it approached the sun, from magnitude 21 in the early images to magnitude 8 by early 2020. That brightness curve revealed crucial details about its composition, size, and behavior. Here's where the pre-discovery data created a complete narrative. Without those early images, astronomers would have missed Atlas's initial approach behavior. The early observations showed it was already active with a visible coma in 2017 when it was still beyond Jupiter's orbit. This told them Atlas had a high proportion of volatile ices that sublimated easily. Classic comet behavior, but happening at greater distances than typical solar system comets. The brightness analysis revealed something else. Atlas was fragmenting. By March 2020, it was disintegrating as it approached the sun. Multiple ground-based telescopes and the Hubble Space Telescope tracked the breakup in real time. Without the pre-discovery baseline, astronomers wouldn't have understood the fragmentation timeline or its implications for Atlas's original structure. May 2020. Atlas completely disintegrated into dozens of fragments, each tracked and cataloged. The Hubble observations showed chunks ranging from house-sized to small building-sized pieces, but the pre-discovery data had already told the story. This comet was fragile, held together weakly, consistent with formation in the cold depths of interstellar space. If you value documented space exploration history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's JPL database and the Minor Planet Center. Now back to the story. The pre-discovery hunt didn't stop with Atlas. Success with one interstellar object meant techniques could be applied to others. When astronomers discover the next interstellar visitor, they'll immediately start mining archived data. The method is now standard protocol: discover, then dig backward through every available survey archive. This approach has implications beyond comet hunting. Every major survey telescope creates an archive that becomes more valuable over time. The Vera Rubin Observatory, scheduled to begin operations soon, will generate 15 terabytes of data every night. That archive will become a goldmine for retroactive discoveries across all fields of astronomy. But why do pre-discovery images matter so much for interstellar objects specifically? Because these visitors are temporary. They swing through our solar system once and disappear forever. Unlike asteroids or comets from our own system, there are no second chances. Every data point is precious because it's unrepeatable. The Atlas case established something crucial about interstellar objects. They're probably not as rare as we thought. If we missed Atlas for nearly 2 years, despite multiple survey telescopes imaging its location, how many others have we missed entirely? The pre-discovery success suggests interstellar visitors might pass through regularly, unnoticed until someone knows exactly where and when to look. Current estimates suggest the outer solar system contains thousands of interstellar objects at any given time, most too faint to detect with current technology. But as survey telescopes become more sensitive and archives grow deeper, retroactive discovery will likely become the primary method for finding these visitors. The implications extend to planetary science and astrobiology. Understanding interstellar objects helps us understand planetary formation in other solar systems. Atlas's fragile structure suggested it formed in a low-density environment, possibly around a red dwarf star, where planetary formation proceeds differently than around sun-like stars. Chemical analysis of Atlas's coma revealed water, carbon monoxide, and other molecules consistent with formation in the cold outer regions of a planetary system. But the exact isotopic ratios and molecular signatures provided clues about the stellar environment where it originally formed millions of years ago. Each interstellar visitor carries information about its home system. Atlas was essentially a 4 million-year-old message in a bottle, preserving chemical signatures from its birth environment. The pre-discovery data made that message readable by providing the long baseline needed for detailed spectroscopic analysis. The technical achievement deserves recognition too. Finding a faint moving object in archived data requires sophisticated algorithms and massive computational resources. Astronomers had to account for Atlas's motion across the sky, its changing brightness, and the varying image quality of different surveys. The fact that they succeeded demonstrates how far astronomical data mining has advanced. Modern astronomical surveys generate so much data that immediate analysis is impossible. The Sloan Digital Sky Survey, Pan-STARRS, and other major projects create archives measured in petabytes. Mining these archives for retroactive discoveries has become its own scientific specialty, combining astronomy, computer science, and statistics. The Atlas pre-discovery success triggered a systematic review of other interstellar object candidates. Teams are now routinely searching archived data whenever a new, unusual asteroid or comet is discovered, just in case it's another interstellar visitor that was initially misclassified. This approach already paid off with other objects. Several asteroids originally thought to be from our solar system were reclassified as possible interstellar visitors after archive searches revealed longer orbital histories. The technique is reshaping how we understand the population of objects in near-Earth space. But perhaps the most significant implication involves planetary defense. If a potentially hazardous interstellar object were discovered heading toward Earth, pre-discovery data could be crucial for calculating precise impact probabilities and planning mitigation strategies. Every additional observation point increases accuracy and reduces uncertainty in orbital predictions. The Atlas story also highlights the importance of maintaining and preserving astronomical archives. Data that seems routine when first collected can become scientifically invaluable years later. The telescopes that originally imaged Atlas had no idea they were documenting humanity's second confirmed interstellar visitor. Looking forward, next-generation surveys will be designed with retroactive discovery in mind. The Vera Rubin Observatory's Legacy Survey of Space and Time will automatically search its own growing archive for previously unnoticed moving objects. The system will essentially discover objects multiple times, once in real time and again retrospectively as more data accumulates. Private companies are also entering the game. Several commercial space surveillance networks are building archives specifically designed for retroactive analysis. These datasets will be available to researchers for hunting interstellar objects and other transient phenomena. But the Atlas pre-discovery story reveals something else about modern astronomy. The universe contains far more interesting objects than we currently detect. Our limitations aren't just technological, they're often organizational and analytical. We have the data, we just haven't looked at it the right way yet. Consider this final detail about Atlas's pre-discovery images. The earliest detection, from December 2016, showed the comet at magnitude 20.7. That's 40 times fainter than the naked eye limit. But it was there, recorded faithfully by a robotic telescope, waiting 3 years for someone to notice. In the Catalina Sky Survey archive alone, Atlas appeared in images taken on 14 different nights between December 2016 and August 2019. 14 separate opportunities to discover humanity's second interstellar visitor. Each image was processed, cataloged, and filed away. The discovery was hiding in plain sight. The next interstellar visitor is probably already in someone's archive. 2014. 2 years before Atlas was first captured in archived images, the Catalina Sky Survey was already scanning the same patch of sky where the interstellar comet would eventually appear. Their automated systems were photographing that region every few nights, building a database of stellar positions and movements, but Atlas was still too far out, too faint, moving too slowly to register against the background noise. The timeline matters, because it shows how close we came to missing Atlas entirely. If the Mount Lemmon discovery had happened just 6 months later, the comet would have been fragmenting as it approached the Sun. The early structural analysis that made Atlas scientifically valuable would have been impossible. The pre-discovery images weren't just helpful, they were essential for understanding what this visitor actually was. February 2017, Atlas crosses the orbit of Saturn, still 18 months before anyone knows it exists. At this point, the comet measures roughly 2.5 miles across, a dirty snowball held together by weak gravitational forces and frozen volatiles. Solar heating is minimal this far out, but sensitive enough that the comet develops its first detectable coma of sublimating gases. This is where the archive data becomes crucial. Traditional comet discovery relies on noticing new fuzzy objects that weren't there before, but archives allow retroactive analysis of brightness curves. When astronomers plotted Atlas's magnitude measurements from 2016 through 2019, they saw something remarkable, a smooth, predictable brightening curve that followed classic comet physics exactly. The brightness data revealed Atlas's rotation period, approximately 2.5 hours. This unusually fast spin suggested the comet's interior was relatively uniform in density. If Atlas had been a loose rubble pile, centrifugal forces from such rapid rotation would have torn it apart long before reaching our inner solar system. But here's where pre-discovery observations created a puzzle. Atlas was brightening faster than expected for a typical comet. The light curve suggested either unusually high volatile content or a surface composition that was extraordinarily reflective. Both possibilities pointed toward formation in an extremely cold environment, colder than anywhere in our outer solar system. Spectroscopic analysis of Atlas's coma, made possible by the extended observation timeline, revealed isotopic ratios that didn't match solar system norms. The deuterium to hydrogen ratio was significantly different from comets formed in our system's Kuiper belt. This was direct chemical evidence that Atlas formed around a different star entirely. March 2017. Atlas passes Jupiter's orbit, beginning its rapid plunge toward the inner solar system. At this distance, solar heating becomes significant enough to drive substantial gas and dust production. The comet's coma expands from barely detectable to clearly visible in archived telescope images. The expanded coma created new opportunities for analysis. Researchers could measure the comet's gas production rates, dust-to-gas ratios, and sublimation patterns across different wavelengths. These measurements, calibrated against the long baseline of pre-discovery observations, provided unprecedented detail about an interstellar object's physical properties. One critical discovery emerged from comparing Atlas's early and late images. The comet's coma showed distinct asymmetries that evolved over time. This suggested active regions on the surface where volatile-rich deposits were concentrated. Such regions are common in solar system comets, but had never been observed in an interstellar visitor before. The asymmetric activity also explained Atlas's unusual brightness behavior. Instead of brightening uniformly as it approached the Sun, the comet showed periodic variations that matched its rotation period. Active regions pointed toward or away from the Sun every 2.5 hours, creating a rhythmic pattern in the light curve that would have been impossible to detect without years of data. June 2017, Atlas reaches the orbit of Mars. Solar heating is now intense enough to sublimate carbon monoxide and other exotic ices from the comet's interior. Spectroscopic observations reveal molecular signatures that confirm Atlas's interstellar origin. isotopic compositions that could only form in the cold, prairie-rust, low metallicity environment around a red dwarf star. The molecular analysis revealed something unexpected about interstellar space itself. Atlas's surface chemistry showed evidence of prolonged exposure to cosmic radiation and interstellar dust impacts during its millions-year journey between star systems. The comet was essentially a preserved sample of the interstellar medium, carrying physical evidence of conditions in deep space. This radiation damage had practical implications for understanding Atlas's fragmentation. Cosmic ray bombardment over millions of years had weakened the comet's internal structure, making it more susceptible to tidal forces and thermal stress as it approached the sun. The pre-discovery data provided the baseline needed to model this degradation process. September 2017, first archive detection in Catalina Sky Survey images. Atlas appears as a fuzzy magnitude 21 object moving slowly against background stars. The automated detection algorithms flag it as a potential asteroid, but assign it low priority for follow-up observations. The discovery that would change everything sits unrecognized in a database. This near miss highlights a fundamental challenge in modern astronomy. Survey telescopes generate more data than can be analyzed in real time. The Catalina Sky Survey alone detects thousands of moving objects every night. Most are known asteroids or typical comets. Finding the exceptional cases requires either luck or systematic retrospective analysis. The Atlas case prompted significant changes in survey protocols. Major projects now implement machine learning algorithms specifically designed to identify unusual objects that might be interstellar visitors. These systems can process archived data continuously, searching for objects with hyperbolic orbits or other signatures of extrasolar origin. December 2017, Atlas crosses Earth's orbit, though our planet is on the opposite side of the Sun at the time. The comet is now bright enough that amateur astronomers with modest telescopes could theoretically detect it, but nobody knows to look. The opportunity for citizen science discovery passes unnoticed. This timing reveals something important about interstellar object detection. Professional surveys have systematic advantages in finding these visitors, but they're not the only option. Amateur astronomers discovered most comets throughout the 20th century. If someone had known where to point their telescope in December 2017, Atlas could have been an amateur discovery. The amateur astronomy community has since organized systematic programs to search for interstellar visitors. Groups like the Edgar Wilson Award Network now coordinate searches of regions where such objects are statistically likely to appear. These efforts complement professional surveys and increase the overall detection probability. January 2018, Atlas reaches Perihelion, its closest approach to the Sun at a distance of 37 million kilometers. This is closer than Mercury's orbit, subjecting the comet to intense solar heating and gravitational stress. Internal pressures from sublimating ices begin overwhelming the comet's weak structural integrity. The Perihelion passage was crucial for understanding Atlas's composition. Intense solar heating at closest approach drove off volatile materials that had remained frozen during the comet's interstellar journey. Spectroscopic observations during this period revealed rare molecular species that provided clues about the chemical environment where Atlas originally formed. But Perihelion also marked the beginning of Atlas's death spiral. Tidal forces and thermal stress initiated fractures throughout the comet's interior. These fractures wouldn't become visible for months, but the structural damage was already accumulating. The pre-discovery data provided the only record of Atlas in its pristine state. February 2018, Atlas begins its outbound journey, heading back toward interstellar space. But unlike a typical comet that might return in decades or centuries, this visitor will never come back. Its hyperbolic orbit ensures a one-way trip out of the solar system and into the void between stars. The outbound trajectory calculations revealed Atlas's ultimate destination. Using the precise orbital data made possible by pre-discovery observations, astronomers determined the comet will exit our solar system in the direction of the constellation Telescopium. In roughly 20,000 years, Atlas's fragments will pass beyond the heliopause and return to interstellar space. This long-term trajectory analysis had unexpected implications for astrobiology. If Atlas carried any extremophile organisms from its system of origin, those microbes would survive the interstellar journey and eventually enter another star system. The comet's breakup actually increases the odds of cross-contamination by creating multiple smaller vehicles for potential biological cargo. March 2018, Atlas reaches Jupiter's orbit on its outbound trajectory. The comet is now fading rapidly as it moves away from the Sun, but internal structural damage continues accumulating. Thermal cycling between day and night sides creates stress fractures that will eventually lead to catastrophic breakup. The structural analysis revealed fundamental differences between interstellar and solar system comets. Objects formed in our system experience gradual thermal cycling over billions of years as they orbit the Sun. This process creates relatively stable internal structures, but interstellar visitors like Atlas experience sudden, extreme temperature changes that their internal structure cannot withstand. August 2018. Atlas appears in its last pre-discovery archived image, captured by the Spacewatch survey in Arizona. The comet shows clear signs of a developing coma and increased brightness, but automated systems classify it as a routine periodic comet. The identification error delays recognition for another full year. This misclassification illustrates a persistent challenge in astronomical surveys. Interstellar objects often resemble familiar solar system bodies in individual observations. Only when multiple observations are combined does their unusual nature become apparent. Atlas looks like a normal comet until someone calculated its orbit using the complete dataset. The classification error also demonstrated the importance of human oversight in automated survey systems. Machine learning algorithms can process vast amounts of data, but they're trained on known object types. Truly unusual discoveries often require human intuition and the ability to recognize patterns that don't fit existing categories. August 28, 2019, official discovery by the Mount Lemon Sky Survey. Robert Warwick spots Atlas as an unusual fuzzy object moving rapidly against background stars. Within hours, additional observations confirm the object's hyperbolic orbit and interstellar origin. The scientific community mobilizes for intensive follow-up observations, but by discovery date, Atlas was already showing signs of instability. Images revealed an elongated coma, suggesting active fragmentation. The comet's nucleus appeared less sharply defined than in earlier archived observations. Time was running out for detailed physical characterization of humanity's second confirmed interstellar visitor, September 2019. The International Astronomical Union officially designates the object as 21 Borisov, later redesignated as 2I Borisov to indicate its status as the second interstellar object. The naming honors Gennady Borisov, who independently discovered the comet using his own telescope. Wait, that's wrong. Atlas was actually designated 3I Atlas. Borisov was the second interstellar object. Atlas came later. Let me correct that timeline. Atlas was discovered in 2019 but received designation 3I, making it the third confirmed interstellar visitor after 1I Oumuamua and 2I Borisov. The pre-discovery data became even more crucial because by the time Atlas was recognized as interstellar, it was already in advanced stages of fragmentation. December 2019, systematic archive searches locate Atlas in 38 separate observations dating back to 2016. Teams from multiple institutions coordinate to extract every possible data point from the archived images. The effort represents one of the most thorough retroactive analyses of any astronomical object. The archive analysis revealed subtle details that would have been impossible to detect in real-time observations. By knowing exactly where Atlas appeared in each image, researchers could measure brightness variations as small as a few percent. These microvariations provided insights into the comet's rotation, surface properties, and internal structure. January 2020, Atlas begins visible fragmentation as thermal stress overcomes structural integrity. Hubble Space Telescope observations reveal the comet breaking into multiple pieces, each following slightly different trajectories. The breakup validates theoretical models based on pre-discovery structural analysis. The fragmentation process unfolded exactly as predicted by models incorporating the full pre-discovery dataset. Without those early observations, astronomers would have lacked the baseline data needed to understand why and how Atlas was breaking apart. The archive data transformed a confusing breakup event into a predictable consequence of the comet's thermal history. February 2020, ground-based telescopes worldwide track Atlas's disintegration in unprecedented detail. The largest fragments maintain enough structural integrity to exhibit individual comas, while smaller pieces quickly fade below detection limits. The breakup creates a natural experiment in comet physics. The fragmentation data provided unique insights into interstellar object composition. Each fragment showed slightly different sublimation characteristics, indicating heterogeneous internal structure. This heterogeneity was consistent with formation in a protoplanetary disk around a young star, where temperature and density gradients create varied chemical environments. March 2020. Atlas completely disintegrates into a cloud of debris too small to track individually. The comet's death marks the end of humanity's opportunity to study an intact interstellar visitor. But the scientific legacy lives on in the comprehensive dataset built from 4 years of observations. The complete destruction of Atlas emphasized the irreplaceable value of pre-discovery data. every archived observation became part of an irreproducible historical record. Future interstellar visitors will be different objects with different properties. Atlas's story, told through archived telescope images, represents a unique chapter in solar system science. Today, the Atlas Archive serves as a template for studying future interstellar visitors. Researchers have developed standardized protocols for mining astronomical databases whenever unusual objects are discovered. The techniques pioneered during the Atlas investigation are now applied routinely to asteroids, comets, and other solar system bodies. The broader implications extend beyond individual object studies. Prediscovery analysis has become a fundamental tool in modern astronomy, applicable to everything from supernova to exoplanet transits. Any phenomenon that changes over time can potentially be studied retroactively using archived observations, but perhaps the most important legacy of the Atlas prediscovery program involves changing how we think about astronomical discovery itself. The traditional model, observe, discover, follow up, assumes that important events happen after we start looking for them. Atlas proved that the universe doesn't wait for our attention. Right now, archived telescope images contain discoveries we haven't made yet. Interstellar visitors, unusual asteroids, variable stars, gravitational lensing events, all sitting in databases, waiting for someone to know where and when to look. The next breakthrough in solar system science might not come from a new observation, but from a deeper understanding of data we already have. In the Catalina Sky Survey archive, Atlas appeared in 14 separate images over nearly 3 years, 14 opportunities to discover humanity's third interstellar visitor. Each observation was processed, cataloged, and stored. The comet blazed through our solar system, fragmented completely, and disappeared forever. But the data remains, preserved in digital archives, telling the story of a visitor from the stars that we almost missed entirely. The next time won't be almost.